Thank you.
Okay, my name's Dan Walsh. Senior tech, one of a senior distinguished engineer at Red Hat. I've worked on a lot of these tools, including Bootsy, which you just saw. Kind of the inventor of Podman. Worked with Docker, worked with.
Okay, my name is Douglas Schilling Landgraf. I've been working Red Hat in the last 16 years on different projects from virtualization, containers, kernel. Then before Red Hat, I was working the first Linux ATM in the solar system. If I'm using the words incorrectly, please allow people correct me. Before that, I was one of those guys from kernel community, helping create those drivers for web cameras, radios, and digital TV. So there is a small chance that maybe you guys running one of those drivers that I have contributed. Get back to that.
Okay, please read out, actually, everybody please stand up for a minute.
Please, guys, please, let's go, let's go, let's go.
I think I went there. Okay, so please read out all text that is in red.
Red.
Try to get it together.
Promise.
You're gonna wait until I see the rest of the statement.
Let's read it together, guys. Let's go.
They're up.
I promise. I promise. Rather than okay, guys.
All on container files.
I promise. Containers or site containers rather than Docker containers. I promise. To give it a 5-star review, please.
All right, I wasn't even gonna put that up, but I think a couple of presentations ago, we saw something on space Ross, and he must have said the Docker adjective like 15 times, which drives me out of my mind. So while he was doing that, I went and ran with Podman rootless mode. I ran the ROS container and was able to run ROS on my laptop in rootless mode. So seems to be a Podman container in my opinion, but anyways, we'll get over that. So we're talking about Podman. Let me get this. Right, myself. Yeah, you see.
Can you get the Zoom bar out of there?
Yeah, what do I have to do? Say, okay. Is there a hide?
You can move it away. You can move it, right?
Just
I'll move it down.
Oh, I see which one.
Then also this one, click on this.
It's not container, guys. That's why you have some problem, you know?
Yeah.
As soon as you cover containers, you'll be easier. Oh, don't worry about. Yeah,
Yes.
great.
Okay, so obviously we're going to talk about Podman and Friends. A lot of it's going to be covering some of the stuff that was in the previous session. Again, I kind of working on container technologies all the way back to 2005. And I like to think of myself. Now it's not working. I like to think of myself as the earthler of containers. Originally I got containers into Fedora. Then I got into RHEL, and then I got into OpenShift. Then I got into OpenStack. I got into RHIVOS, Red Hat in-vehicle operating system. And now started working on Bootsy. And now I work on Red Hat AI, which is also containerizing AI models. So basically, I figured out I developed a hammer, and now I see the entire Linux world as Linux. But basically the idea, what I really truly believe in, and again, I come from the SE Linux world, is that SE Linux was an incredible tool at controlling what processes do on the system. We built all these tools around it. The problem is it was very difficult to use. But once we came up with the concept of containers, all of a sudden we started sticking applications into boxes, and we can actually control what those boxes do on the system. All right, so and to give you a proof point on that, every one of us carries cell phones in our pockets. If you're running Android, they're all running SE Linux. And if you're, but basically that's just containers, right? Apps on a cell phone, and nothing more than containers. I wrote the book called Podman in Action. If you want to go buy it, you can put some money in my pocket. Sadly, Red Hat actually bought the book also and gives it away for free. So if you don't want to put money in my pocket, you can download the PDF and use it. Okay, so we've been talking about putting containers on edge devices, right? So the RHIVOS effort is really integrated group inside of Red Hat called containers on edge, or basically getting to edge deployments. And we're not talking sprinklers, but we're talking large devices, right? So windmills, trains, space, cars, everything. All sorts of military vehicles. So really talking about getting computers out on the edge and getting them, and in my, a lot of these systems, we want to make them cookie cutter, right? So we want to make everything the same. We want to basically not have snowflake operating systems all over the place. You want to have everything unified and then have the applications delivered as containers. Again, going back to cell phones, right? Your cell phone operating system is they're almost all exactly the same. They're very minimal operating systems. So how can Podman and Friends help in critical missions? Well, first of all, it's OCI compliant. That's why I don't like Docker. OCI, Open Container Initiative, is the standard of all containers in the world. Whether you're running them in things like Kubernetes or running them locally on Podman or Docker or any of the other tools out there. We can do a minimal footprint, so we can actually start to shrink down these applications to just what you need inside of the application, eliminating the footprint and minimizing the size. With container tools like Podman, you can run everything rootless, so we have better security separation. You don't have to run. I think earlier we were talking about something running as root on the system, which as an old security guy, just scares the hell out of me. So we run things as rootless, support out of the box. Things like namespaces, SE Linux, C groups, seccomp, all the rules of controlling what's going on in the process, from security separation, resource constraints, and then namespaces to give you the separated view of the system. And CNCF donation. So we're all here at Elisa here, and basically 2 weeks ago, I stood on the main stage at KubeCon, looking fatter and older than I would have thought, but life is what it is. And we announced at that point that we were donating Podman to the CNCF. So, but we didn't only donate Podman to the CNCF, we also donated a project called Podman Desktop, which was demonstrated earlier. So Podman is all about running containers in the world on edge devices or local systems, any way you want it, building them. Podman Desktop is about a free, fully open source and totally free as in beer, as well as free as in Libra, ability to run and build containers on Macs and Windows. I'll talk about that in a second. And then Boot C. I got the sweatshirt on. Boot C, as we covered in the previous session, is all about building operating system as containers, right? Using the same tools to build your applications as you're going to be designing and building your operating system. So I'm going to be talking about Red Hat in-vehicle operating system. People think cars, but it turns out that planes and ships and space are all called vehicles, right? So RHIVOS is Red Hat in-vehicle operating system. There is a open source component to it called the CentOS Automotive. And so everything we're going to be talking about is fully free. You can get downloaded. But obviously, if you want to pay for it and help pay our salaries, then you can use Red Hat in-vehicle operating system. So it's image-based Boot C, as we saw in the previous demonstration. It's a binary distribution based on Red Hat Enterprise, so it has the same support cycle of it. At Red Hat Summit this past spring, we announced 2 new ways of dealing with Red Hat operating system. There's image-based, and then there's package-based. Package-based is what we traditionally, and image-based is based on Boot C. So it's basically treating the operating system as an individual image, and then RHIVOS ends up being a specific version of that for running in vehicles. It supports out of the box the real-time kernel that we're talking about a lot. So the real-time kernel is on by default on RHIVOS. It is going to be a Boot C based operating system. So design a minimal OS for your, as a container. Same OS platform everywhere. Again, we want to have cookie cutter. So if you're gonna get into the image business, you want to have all of your satellites exactly the same base operating system, and then you add everything as containers. Atomic updates, that means that when you update the operating system, it doesn't really get updated until you reboot into the new kernel. So it's not gonna be updating on the fly, you're gonna download the packages, but you won't see the packages until you reboot. Applications built and tested and deployed as containers. The beauty of this is now you can build your operating system and test it as a container, and then you build all your applications, and you can treat everything separately through all sorts of CI/CD systems. Basically take all of the cloud native technologies that have been built for things like Kubernetes over the last 10 years and take those and apply them to your edge devices and to your vehicles. Finally, I'm going to talk about a new file system that we developed for this environment called ComposeFS. So ComposeFS is also being donated to the CNCF, and ComposeFS is a brand new file system that allows you to detect when errors happen in the file system. We had a session earlier today that was talking about problems with radiation and corrupting the system. Well, on a normal Linux system, it's very difficult to figure out if a file has become corrupted, right? So something happens, a piece of radiation comes in and actually modifies something in the file system. Well, when you're talking functional safety, we're going to be talking about in a little while, we need the system to discover if something has become corrupted. Okay, and what ComposeFS does is basically allows us to apply things like FS Verity, which is the way the kernel can basically check some individual files on the file system, and then when it goes to read them, check that the checksums are not changed. So this is from a security point of view, allows us to discover if a hacker has gone in and modified parts of the file system, or if an act of God has gone in and modified parts of the file system. So it's a brand new file system written by Red Hat over the last year to basically allow us to get towards functional safety support. Again, RHIVOS is going to be very container friendly. And one of our goals with donating Podman Desktop to the CNCF is to basically allow people to build their applications on the desktop and then go out and test them and CI/CD systems on it. One of the things that was brought up in yesterday's meetings was a lot of the developers at NASA would like to be able to sit on their laptops and develop applications. Well, the Docker Desktop and Podman Desktop are all about building applications as containers and then again firing them off into CI/CD systems. So Podman Desktop works on Windows, works on Macs, works on Linux. It is build your container applications from the desktop and then software independent from the base operating system. So another thing that was brought up yesterday in some of the meetings is some of the hardships that you have is trying to pick out particular, tool chains that you want to run. Well, with containers, you embed the tool chain or the tool, the libraries and things like that inside of the container. So the operating system doesn't have to be shared between all the applications. And that allows the operating system application suites to work at different levels than the individual containers. And that's why, in a Kubernetes cluster, you might have 15 different operating systems running different versions of the library, different versions of each operating system, things like that. Next thing I'm going to talk about, I'm trying to rush through this as quickly as possible, is functional safety. So I worked a couple of years ago, for a couple of years on functional safety and looking how we can use container to provide functional safety process reducing risk. I think most of the people in this room know what functional safety is. So basically it's trying to, basically protect the system from unsafe code and really looking at how the operating system, how do we get an operating system to be classified as a functionally safe operating system? So traditional functional safety comes down to systems designed, documents are written, and a lot of this we talked about earlier today. And then code is produced to meet the requirements, and then tests are written to guarantee the code. Well, I think the session on the kernel, which I thought was fascinating, talked about how, basically retroactively going in and writing the design documents. And then, it was kind of a cool talk. And this is one of the problems we've had with trying to get, Linux to be functionally safe, right? No one wrote any design documents. Everything evolves. I talk about this as creationism versus evolution. right? Linux is an evolution operating system. It evolves, right? No one's really designing it. It's just people coming in and say, I need this new feature, and they're adding it. As opposed to some godlike creature that comes in and says, you know, here's the requirements and make the thing match the requirements. So getting Linux functional safety really means people trying to get people to think about the way the operating system has been developed and done over the years and get, you know, there's no real design document. So how do we justify it? How do we prove that the kernel is safe? How do we prove that system D and other parts of the thing is safe? And we're working with the creditors right now to do that. So, I'm gonna quickly switch case a little bit here, but one of the things when we talk about containers, you know, could we explain why we're not using OpenShift in the vehicles? Well, Kubernetes, OpenShift is Red Hat's Kubernetes applications, Kubernetes plus. So Kubernetes in a vehicle. Sound like a good idea? The problem is Kubernetes is based on eventual consistency. System might be in a consistent state, but is processing towards it. So you know, Kubernetes was originally designed around the concept of, I need a web service started up on 3 different places, and eventually I'll get a website up in 3 different places. So the braking system will eventually activate is probably not what you want. You know, so we need a state machine with in vehicle, or when you're using functional safety, you really can't say I want it eventually to be in a good state. I need it to be instantaneously in good state. So we actually wrote an article a couple of years ago, basically saying why Kubernetes is not the tool, even if you're going to run on multiple services in a system that has to be functionally safe, because of this concept of eventual consistency. Oop, let me go back.
Oh. There's a,
Oh, go, you can take a picture.
that's right, please.
Take a picture.
Oh.
Okay. So when we look at the way an operating system, we think of system D as being a host orchestrator. So system D is a state machine, right? It basically switches from one state to another when you're running system D. So you have application profiles, system D unit files. One profile is for one more application. The application is is basically mapped to a single system D service, and then a capability is to switch from different profiles. So that is very vague, but when you think about when you boot up an operating system, so once you boot up, you're in the first state, and that's going to start certain services on the system. But then when you get up to a next state or the next run level, you're going to get to a network state, and that might turn off some of the boot states and turn on other applications. And then when you get to multi-user, again, different services are going to be started and stopped during that boot phase. And finally, you get to graphical user, and again, services are starting and stopping, but system D is moving from different run levels. So if you're looking at a vehicle, specifically a car, we want to do the same type of thing with RHIVOS, and that we want to have one profile defining one or more applications. Exactly the same, but think more of this as when you get into the car and you start the car, you're going to have certain services starting and certain, there's no services stopping. But once you go from start and you throw the car into reverse, you're going to have the backup camera turn on, some of the sensors in the back of the car, and you're going to move from a different run levels. Finally, when you put the car in drive, the backup camera turns off, the back sensors might go off, and the front sensors turn on, and you're basically having different services changing, and that's all based on system D changing the services. And we want each one of the services to be run as containers. So in the previous section, we came up with a new term. So what do you call it when you squash? If you stomped on top of a kubelet, what would you get? Okay, you get a quadlet. Okay, so that's where the name comes from. So it's a Kubernetes squashed. Quadlets is a way to define systemd unit files, systemd services that run containers. So this is running Podman inside of containers. And here's we have a simple example where we're going to run basically UBI 9 minimal with the sleep 1000. And it's basically just looks like, here's the image, here's the command. They're going to run inside a container. And this is uses this concept in systemd called a generator. And what a generator does is reads that file and then generates a real systemd unit file. And it runs a this ugly line down here, but in the bottom red line, you'll see a very complicated Podman line here that embeds the way that system D wants to monitor a container running inside the system. So you see SID file. Let's see if I can sideways a little bit. So we had that one line.
Yeah, that's really.
Stay there for a second. You can see down here, it's a fairly complex line, but it does things like sets up C group split, which allows system D to share it, says how to notify the system. But basically, it's building in our intelligence about the Podman team's intelligence of how system D would want to monitor a container. But we go from your point of view, you just have to write the simple line. So we're going to get a little bit more into Quadlets. So we're going to talk a little bit about freedom from interference. So one of the components of functional safety is freedom from interference. So in the freedom from interference means that you're going to be running multiple different applications on a system at the same time. Some of them are going to be safety critical, and some of them are going to be not so safety critical. In the functional safety world, they call that QM, or quality managed. So your non-safe tools are sometimes called quality managed. And then in the automotive world, they're called ASIL, which is somewhat mapped to sort of what we talked about in aerospace being instead of A, B, C, and D, there's also A, B, C, and D. In this case, we talk about ASIL B versus QM. QM is basically the lowest level tools that are run that you don't need to worry about functional safety. So examples of ASIL applications are things like blind spot detection. My bad example of the braking system, for instance, collision warning systems. All these critical systems that if they fail, the car needs, basically has to go into a safe mode. Basically, the car has to shut down. But then you have quality managed applications that you're running inside your vehicle, and these are things like your navigation system, climate control, windows, things like that. So we created a project called the QM project. And what we wanted to do with QM was basically to give a developer an easy way to install software onto a system that was guaranteed to be isolated from the ASIL environment on the system. So the QM project defines a Quadlet that builds this type of environment. So you can see up here, the green part of the environment is all the processes that are running at ASIL on the system. So all of the critical applications that are running on your application, functional safety point of view, and you'll see that there's a separate Podman database here. So these are, you still run your containers on the system. We believe that you should run all your applications as containers, but these containers will be isolated from the containers inside of the QM. Inside of the QM is basically almost looks like another operating system. Almost looks like it could be a VM in the system. But what we want to do here is we want to run as containers in there. Now, inside of these containers, you can run VMs. Okay, so one of the questions that came up earlier is I talked about the Linus Torvalds article that just came out like a week ago. I wrote the same article about 10 years ago, so I kind of chuckle out of it. So in certain cases, VMs isolate better than containers. But sometimes you want to be able to interact with the processes inside the container. You want to monitor those, you want to control those processes, or you want to have certain types of operations going between them. So with the QM, the idea is that an application could just be installed into this environment, and all of a sudden it is being wrapped in a container technology. And you can run containers within containers. So that's why Podman, this has a full separate system D running in it and everything else. So isolate the QM environment with the Podman Quadlet. And this is what a Quadlet would look like that would define a QM on your system. This is the actual one that we ship. And it has some suggested constraints here. First of all, we identify it as QM slice, so that you can actually use system D commands to basically shut down all the processes that are in the QM or to lower their privileges, lower the amount of CPUs that they have. You can actually isolate all of the processes inside of the QM to specific CPUs on the system. So we talked earlier and we were talking about maybe I want to have 2 or 3 CPUs dedicated to certain processes, certain applications, and then isolate all of the non-critical applications to specific CPUs. And these are all things that are available in Linux kernel. So these are totally using C groups, but it becomes a lot easier for human beings to actually understand how to be able to do this using Quadlet's system D constraints. You can do things like CPU weight, which basically tells processes in the QM that they only get half as much CPU as processes in the ASIL. And this can be adjusted on the fly, and then you can subdivide those. Similar IO weights for controlling how much disk access they get. So it says that it gets 50% disk for every 2 disks access for ASIL. You'd only get 1 inside of these, and you can play around with these numbers and do it. Finally, the other thing you have to worry about is memory constraints. So if a process inside of the QM grows to take up too much memory, we call this the Katniss Everdeen option, which basically says, pick me to be killed. So the Linux kernel basically has a thing called killer and out of memory. Killer basically goes out and starts shooting people in the head when it starts to run out of memory. Well, with the Katniss Everdeen, we can basically say, kill processes in the QM before you kill processes in the ASIL. Not only that, but we actually set up the containerized process inside of the QM to be shot. They even step in front of Katniss to be killed first before the process. So you want the container processes, so the entire container is killed before the entire QM gets killed. So you can set up all these constraints, and they're all based on the Linux operating system. So at this point, I'm gonna
Thank you so
pass
much,
the
Doug.
clock.
Thank you so much. So how it looks like, just showed us details, technical details, how it looks like, what it will look like in the car in the future with containers. Containers will be these applications as example here, or will be nested containers running under QM, as Doug mentioned. And here, as you can see below, there is the base, which is a Red Hat Linux CentOS, that you have Podman, systemd, SLinux, ComposeFS run, and all the main components that we believe that are important for a secure car OS. Then a little bit up, there is a layer that car manufacturers can simply add their software in the like a Lego. So you can put their software once, then everything is shipping out of the box inside containers. That's the goal. But we are here today to speak about space, right? So how it looks like to be, how would it be looking like to have a space grade Linux, as Michael showed us here yesterday. So we believe that as we speak about containers, and also we can use this experience and image that we are creating, and this OS that we are creating as a base. So we can still use QM, Bluetooth, kernel, all those components that we are using as base. So I would love to, me and Dan, we'd love to discuss with you guys, because I think we believe that there are missing parts here. The documentation, guys, is one that I would like to see there. I really love the idea, but we don't have time, right? We are in a rush here. Have a few demos to show you guys. So the first one is about, okay, talk is cheap, right? So you guys speak about security, Podman, you guys are secure, so show me how it looks like. So this is just one example of hundreds of thousands of tests that we execute from the kernel, on the base, until the high level from the OS. So we have a bunch of tests. So let's imagine that we are running a car, then we basically got attacked by a hacker, and then he got inside the QM container. It's a nested container. It's running one application, right? Then he's root, right? So his idea is, let's make money because this car is an electric car. So meanwhile, the owner is sleeping. I can make money. I can use Bitcoin or another, coin that is available today. So from 5 a.m., from 9 p.m. until 5 a.m., meanwhile, the owner is sleeping, the car is making money for the hacker. So he's trying to do that, but actually, what happened is that our OS, RHIVOS, was able to detect it, and then SLinux takes the wash for preventing it. So SLinux defend us, okay? But there is a but here, guys. There is a new trainee in the company that updated the software to disable the SLinux. And guess what? What happened now? We disabled the SLinux. Come on, anyone gonna guess here? It updated all the cars globally, and all the cars will be with the SLinux disabled. Do you guys believe this hacker will be able to mine Bitcoin or any other coin in your OS? Anyone try, or otherwise you go ahead because we are in rush. So are you going in rush? No, he's not. He's not able because our OS and Podman and SecComp is able to prevent this attack. So he's here is just a joke. Like, have he prevented the attack? Actually not. So this is the solution, how we prevent this attack. Even with the SLinux disabled, we prevented this attack. So ROS here to stay as secure as possible. We are doing, as I said, hundreds of thousands of tests to prevent those attacks and much more.
So, that's exactly. You had 70 plans for tooling to help define the SecComp policies for container.
Yes, definitely. We can talk a little bit more. We are rushing here. We are really rushing. Okay, so now getting back to space, we are just speaking about cars just because it's connected, right? We are using the OS that we are building for the car, the next generation of the cars. Now we're speaking about space, right? Here, we are NASA to speak about this. So can we use the RHIVOS or CentOS Automotive for this? Yes, we do. So how can we do this? I was thinking like we should start creating maybe a library or framework, you know. I know there is out there other frameworks, but we can start creating rapid launch, right? Like the base for all the vendors for going to space. After that, what I created was, as you guys can see, I have here all the vendors, I mean, not all the vendors, but some of the vendors going to the space. Blue Origin, Boeing, Lockheed Martin, NASA, and SpaceX. Why? Because every single vendor here, they can use this class as base and then implement their specific method for that rocket. So if they have payload or don't have payload, or going back home or not going back home, it's specific for them. So I believe, and as well, that if you're going to do this as a framework, as together as we are planning here, then maybe this is a good start. Next, rover. So going to Mars, we need to. How many? How many minutes we have?
You're 11 minutes over your estimated.
Oh, 11 minutes. Okay. I talked with the guys here. They said that I can continue a little bit. Yeah. I promise that really fast. So rover, the next thing we need to go to space, you need a rover. So going to space just to ship a rocket there doesn't make sense. We need a rover. So I created also a class that can be used as a base, right, for rovers, which basically is an unmanned ground vehicle that if the manufacturer follow this specification, we can control any rover, okay? And this one here, as you can see, is a rover that we have tested. There is another version that we can attach here cameras. This is a Raspberry Pi. It's running RHIVOS here, right? So I have more details later. Here are some methods that is already implemented there. Like it's also integrated to ROS2. The next one is the distribution that we need a Linux distribution, right? So we are here speaking about RHIVOS and CentOS Automotive. Just example, running RHIVOS, really running RHIVOS, putting in this device here. Can you guys help me? Whoa, cousin, right? Oh, it's recording, guys. Help me, please. So the code, some code is available here in the Fedora, right? So we are moving the code to there. So if it's not complete or something missing, give me a pardon. I will update soon with Leonardo. Okay, this is about framework. We can speak later. We also integrated ROS2 this demo these libraries. So we spoke about a bunch in the last 2 days here about ROS integration frameworks. Guess what? We already thinking about this and they already implemented integration. Here I explained how it works. Is basically we send message in the device in the ROS client and ROS engine to ROS, right? The middleware. And then talk to sheet, right? Show me the code or a demo in this case. And this is what you are looking like right now. Oh, there is no sound? Oh, we need sound. Oh. Okay, but later you guys can.
Undo the sound mute thing.
You see the mute?
See that mute there? Click on mute.
There you
Okay, let's start again. Because you work very hard to make this happen. Okay, guys, let's start again. Let's start again. Can I start?
Yeah.
Can I go?
I'm good. Switch.
There. And we.
Try it out, see what's going on. I'm here for the questions, okay? So we are about to launch a rocket, but before launching a rocket, we are already preparing this, like make sure there is no leaks, right? This is really running on top of Rust, is a Red Hat stuff. And we are already checking for cracks in the rocket, really checking for leaks, right? So these are really, really real stuff. It's not, and also using open source, ROS, everything that you can imagine, AI, right? NVIDIA, everything that you can imagine. You can go to the details later if you want. So let's go together, guys. 8, 7, 6, 5, 4, 3, 2, 1, go! But wait, there is more. There is more. There is more. Not 9 months later, because we have a payload. And when we are landing, there is NASA guys there waiting for us, recording in 8K. See? And here is running Podman. We are running communicating Podman with those devices, and they are working. This is my house. That's why you see some sand. It's like Mars, but it's where it's recording. Just to complete, we're almost there. Sorry, we are crossing the time. How can I go there? Oh, Fedora Robotics, led by Leonardo Rossetti. Please contact us. We are all about robotics for all the distributions, not only about Fedora, but we are for everyone. I would like so to thank you, NASA, Elisa, Linux Foundation, Dan Walsh. He's a legend for us, for my generation. Thank you so much for accepting help with me, Dan. He's a legend. Also, to like special thank you, NASA. I'm from Brazil. It's not very simple, to come and live here in US. And you guys from NASA always inspire us, right, from other countries. So this is a statement from me, like please keep leading the path to space and then make us dream of in the possible, making possible. This is what I believe in you guys. And this is my daughter, this is my home, trying to teach her This is one of my daughters. I have many kids, many. Yeah, it's many kids, many forks. Teaching her the open source value, the culture of Red Hat, and also the robotics. And finally, there is more. Just a little bit. Behind the scenes, there is always something happening. Come on, in the red hat. Could it be in the grass? Come on. Okay, I need new red hat, new fedora. So thank you so much, guys. Thank you, Don. Thank you.
There's a few questions online. The last one is, does ComposeFS support the variable?
Yes, it basically ComposeFS takes ROFS and basically creates a file system out of it, and then uses D and Verity on top of that newly created file system to guarantee separation.
Another question is, do you think running QM on the same kernel as that ASO up to D will actually work in the near future? The spinning CPU, of course, sounds quite high level, even that they still have a lot of low level interactions, examples, share resources.
So QM runs right now with real time. So it's, yes, I mean, that's the way we designed it. If you want to have total separation, basically a VM. For instance, we run in RHIVOS, we run the Android auto drive as a VM inside of the ASIC. What someone talked earlier about, actually you were talking about lightweight VMs. So we also have a tool called LibKrun, and LibKrun will run a container in a KVM separated environment. So basically it runs the kernel, and the kernel executes the primary process of the container. So it's about as lightweight you get without going all the way to microkernels or whatever. What's that? Is that like the whole KVM? Yeah, it's basically use Krun, and there's another thing called Krun Kit, which is also based on LibKrun. So, but basically it's a kernel plus a container.
Awesome. Any other questions?
So on the topic of System D, I don't know quite how enthusiastic members of the space industry might be about running just a Linux with System D. Maybe they are, maybe they're not. But middle ground I see is running containers off of a flight software framework, whether it be F prime or CFS or something. That I meant to ask you earlier. You were the author of C running, because I thought that was how you.
So a person, well, I'm gonna say on my team, but he still runs Reds. He's named Giuseppe Scrivano, and he's the guy that wrote C-Run. And actually, he was the one that sort of invented the concept of ComposeFS.
Okay.
So, but C-Run and Run C are two OCI runtimes that run underneath.
One C based, one O based.
Right, C-Run is C based, and it's lighter weight and faster.
What I'm interested in is the library aspect, using C-Run as a library from a flight software framework. So I'm curious.
C-Run is an executable, so it's not a. So C-Run, so there's, yes.
Right, I know it's used as an executable.
Right, but you can link things to C-Run. C-Run basically has a ability to process an OCI runtime specification. And then we can call out to other libraries, if you want to use different types of container technology, like LibKrun, which is also based on, Krun is based on C-Run plus the LibKrun library. C-Run uses the standard library. There's a LibWASM, so it can run WASM library, WASM workloads underneath a container. So Podman can run all of those different types of containers. But I don't know. What are you after here? So you're asking about C-Run in a way that doesn't make sense.
Is probably a little controversial,
Right.
Eliminating System D, trying to run what you're talking about without.
So Podman doesn't require System D.
Right.
So Yeah, so you can run a Podman container on the system.
Replace system D with Bash if you want to.
No, yeah, but absolutely.
Yeah.
What I'm interested in is, what I'm also interested in is tying in some of the aspects of process management, keeping an eye on, or just integrating CFS command telemetry with running containers in
Yeah.
a way that, well, you could certainly do it by just running an executable background and then parsing, basically grabbing the text output or the JSON output of.
So Podman can also run as a service too. The Podman can run as a service. You can talk to it as an API server, similar to Docker. But one big difference between, if you don't understand, if you know Docker, you don't know Podman. Podman works off the concept of forking exec, whereas Docker is a client server operation. Most people run Docker daemons as root on the system, and that, you know, I used to work on Docker and it used to make me sick.
Yep.
Yeah.
And so Podman is a fork exec model, so the container runs as a child of Podman. That's why Podman runs so well under the system D, whereas Docker never ran well under the system D, because that basically it was going through a different process running up the system D. System D couldn't keep track of it. But yeah, you could, one of the big beauties of Podman also is that when you run a container, Podman can go away. Whereas Docker never goes away, right? So Podman goes away. It's a little program called Conman. Just a container monitor.
And we had a question online there.
Yep.
Hey, Matt, go for it.
In that ASOL QM diagram that you guys had up,
Yes.
so I'm assuming in those cases it's KVM type 2 virtualization if you do end up using it, right?
So by default, we're just using container technology to do the
Right.
isolation. But
Has there
if
been
you want to use KVM separation, you can.
Has there been any studies on, I guess, just the time and space isolation aspects of that, considering those are, in either case, it's all still processes scheduled on the main kernel? Like, has functional safety done any of those sort of threads or slices through the system?
So we're doing tests. Yeah, we are doing freedom from interference tests on those processes. So I mean,
Okay.
functional safety is all about individual processes, so you can judge, but what we're trying to do is do a freedom from interference check to make sure that the processes in the QM do not interfere with the processes that require functional safety.
Do you know
So-
if any of that work will be published?
It's all published. Everything
Everything.
that does is in the public.
Open source.
It's all open source. It's all, if you go to the live QM, you'll find all the tests that we're running.
Okay,
Plus all the tests of the kernel. I mean, basically, we're relying on C groups for isolation. We're relying on SE Linux. We're relying on the seccomp. So we're relying on all the different features of Linux kernel. Now, when Linus Torvalds talked in his article from a week ago, I think it was November 9th, or December 9th, it's December, isn't it? December 9th, he talked about KVM separation versus, he called it Docker containers, so I'll have to get him.
We need to talk over him.
Yeah, but
Hey, Linus, come on.
he basically
Podman.
stated the obvious in that, you know, if there's a bug in the Linux kernel, then all bets are off. But that's pretty much just about anything, you know, if I can figure out a way to break out of the Linux kernel and I'm relying on the kernel to give me separation, then I have a problem. That's why KVM separated containers are better. Or if you are totally worried about that type of isolation. But if you're, in general, sometimes that causes more trouble because now you have to deal with memory, you know, you have to do memory allocation and all sorts of props that you have in virtual machines versus containers are just general processing system. So, you know, in the case of where we have a individual processes run away inside of a VM, you have to kill all the processes in the VM. If it's in a container, you just have to kill the container that's running out of memory. So there's cost and benefits to running containers versus VMs. And I always like to tell people it isn't a zero-sum game. You can run containers inside of VMs. You can run VMs in separate machines. You can go up and down the stack. My way I'd like to explain containers versus VMs is when you're looking at physical safety, I look at houses. So I did a coloring book called the Container Coloring Book years ago. And if you said, I want to live the safest way possible, then you live in a single house separated from everybody else. So if you want to run, the most safe way of running an application will be in a separate physical system. If you want to run the second safest way would be to live in a duplex where you'd have a sheer wall with it, but you'd have different entrances. That's what a VM is. VM has this shared, interface to the kernel. A container is more like living in an apartment building where you have a single point of failure. That's the maintenance man who carries all the keys got mugged, then he potentially can get into you. And then you get to the next level. If you're not there, then you're sleeping in a hostel, which is basically everybody running containers, everybody running processes without containers. And then the last one was if you're running without SC Linux on, then you're sleeping in the park. So that's the way, it's a good way to visualize where containers, but again, you can run separate physical machines with VMs, with containers and SC Linux on and run, isolate your processes that you don't trust from each other using different levels of separation. So anyways, any other questions? I think there's a closing mark. We were like half hour over right here.
Thank you so much, guys.
Thank you. Right, everyone virtual, thank you so much, and we'll see you tomorrow. Bye.
Especially to those which stayed from Europe.
Yeah.
Yeah.
Like 11 PM. So thank you.
Bye.
Yeah, thank you.
Stop recording now.
Thank you.